Hello. Today we talk about plane waves in various types of media. While talking about the visualization of the plane wave, I said something about in phase. I said E and H are in phase because it is a lossless medium. I also said eta is square root of mu upon epsilon and it is purely real. Today we will express these concepts in terms of equations so that we understand the nature of electric and magnetic field. In fact, the relationship between electric and magnetic fields in various types of media. Now let's take the equation for gamma and eta. Gamma is square root of sigma plus j omega epsilon times j omega mu. Eta is square root of j omega mu upon sigma plus j omega epsilon. We know these results. If you don't remember it, please go back. These are very important fundamental results. We need to keep remembering this. Now, a lossless medium is characterized by, yes, you're right, sigma is equal to 0. If sigma is equal to 0, gamma will be square root of j omega epsilon, because sigma is 0, times j omega mu, which is j omega square root of mu epsilon. We call it j beta. Beta is omega times root of mu epsilon. That's propagation or phase constant. Okay. Velocity is given by omega by beta. We have also seen this. This is 1 upon square root of mu epsilon. We know this result. Nice result. What happens to eta? Since sigma is 0, it's again turns out to be square root of mu epsilon, mu upon epsilon. So eta is a purely real quantity. Nice. And therefore, Ex and Hy are in time phase. They are always in time phase if the wave is propagating in a lossless medium. Correct. Now what happens to if the medium happens to be a free space? Mu is equal to mu naught, epsilon is equal to epsilon naught, and we know this standard famous result. Velocity is 3 10 to the power of 8 meter per second and eta is 376.73 ohms. Good result. Remember, good to remember, very useful result. Okay, if it's a lossy medium, gamma is complex because sigma is not 0 and eta is also complex. So there are multiple ways to specify the properties of the medium. One is via sigma and epsilon. Other way is representing in terms of epsilon prime and epsilon double prime, or epsilon prime and tan delta. Yeah, we remember that. I thought it is good to do a quick recap of it. Start from Maxwell's equation and we take out j omega common from the electric field expression. Then we get j omega times sigma upon j omega plus epsilon. Look at this. This could be represented as a complex epsilon. Therefore, we can write this as epsilon c equal to sigma upon j omega plus epsilon, and which can be written as real part minus j times an imaginary quantity, which is epsilon double prime. So epsilon double prime is given by sigma upon omega and epsilon prime is nothing but epsilon itself. This can also be written in terms of epsilon prime and tan delta, where tan delta is called the loss tangent ratio of epsilon double prime by epsilon. So a material can be specified by a doublet, either sigma and epsilon, or epsilon prime epsilon double prime, or epsilon prime and tan delta. Any one is fine. It represents the same kind of behavior. Given this information, gamma becomes j omega square root of mu epsilon c. Straightforward result. Don't have to really scratch our head a lot. And eta becomes square root of mu by epsilon c. Did you notice what is beautiful in this result? If the medium is lossless, gamma is j omega square root of mu upon mu times epsilon, purely imaginary quantity. And eta is square root of mu upon epsilon, purely real quantity. If the medium is lossy, then gamma is j omega square root of mu epsilon c, very easy to remember. And eta is square root of mu upon epsilon c, very similar to what we saw in case of a lossless medium. So this is the power of writing in terms of epsilon c rather than writing in terms of sigma and epsilon. Okay. Uh, when the time comes when we need it, we'll use that kind of representation. But once again, we'll define what is called as a low loss medium. We had seen what is lossless medium where sigma was 0. Now we define a low loss medium where sigma is very small compared to omega epsilon. If the conductivity of the medium is very small compared to omega epsilon, then that medium is defined as a low loss medium. Typically, we can see such medium, physical medium, real medium existing or satisfying this condition at higher frequency. As omega is larger, as we keep going higher and higher in frequency, this condition gets satisfied more often and easily. Now, if sigma is very much smaller than omega epsilon, can we think of low loss medium's definition in terms of epsilon double prime and epsilon, or in terms of tan delta? Yep, sigma is very small compared to omega epsilon. Therefore, tan delta must be very small compared to 1. Or epsilon double prime must be very small compared to epsilon prime. If any of these conditions is satisfied, we say that such a medium is called a low loss medium. Now we ask the question, if the medium is low loss, then what happens to gamma and what happens to eta? Of course, they're going to be complex, but gamma is j omega square root of mu epsilon c, and we'll see what happens to this under the condition that sigma is very small compared to omega epsilon. Of course, epsilon c is epsilon prime minus j epsilon double prime, and gamma therefore can be written as, we take out that mu times epsilon prime common, 1 minus j epsilon double prime upon epsilon prime. Think about it, look at it, make sure this is correct. In these videos, what I tend to do is, whenever I get a result of this kind, I jump very quickly, but you pause the video, make sure this is indeed correct. This is very important. If you think that it requires an explanation, post a note on the home page or ask me in the class and I'll explain this. Now we know that epsilon double prime upon epsilon prime is very small compared to 1. That's very important one. Under that condition, we have an approximation. 1 minus x to the power of half is approximately equal to 1 minus x by 2 minus x square by 8, and so on. We take the first two terms only. And then we can write this result as an approximation, which is j omega square root of mu epsilon prime 1 minus j by 2 epsilon double prime upon epsilon prime. Looks interesting? Yes. What's very interesting in this is, you can write gamma as some real quantity alpha plus some imaginary quantity beta, which is equal to omega times square root of mu epsilon prime. Hey, this is interesting. If you have a low loss medium, propagation is constant is complex, but its beta or its velocity is something very similar to that of lossless medium having the same permittivity epsilon prime. Oh, this is a very useful result. So this will have a propagation constant which is, phase velocity will resemble that of the medium without loss. But propagation constant has an alpha, therefore the plane wave travels with the speed, same speed as that it would travel in a lossless medium having the same epsilon prime, but as the wave propagates, its amplitude decreases. This is an approximation, don't forget it. This is an approximation because we have said epsilon double prime upon epsilon prime is very small, we got this kind of a nice result. If this were not to be true, then this won't work at all. Now, what happens to eta? Yeah, exactly the same story. You write this epsilon c as epsilon prime minus 1 minus j epsilon double prime upon epsilon prime. What happens next? Yeah, you take the denominator to the numerator and call it as to the power of minus half, and we are going to make an approximation once again. And which approximation this time? 1 minus x to the power of minus half. is 1 plus x by 2 plus 3 by 8 x square, etc. A pause, a big pause. My sincere request to you all is stop the video now, have a glass of water, take a break, derive these two results. 1 minus x to the power of half and 1 minus x to the power of minus half given by these two approximations. You can use Taylor series for this. Please derive it and remember that this will be very useful, because if I give you a problem where that approximation is not there, you should be able to derive the approximation from first principles. Correct. Let's get back. Then it is not very difficult to show that it is eta is square root of mu epsilon times 1 plus j half epsilon double prime by epsilon prime. Therefore, Ex and Hy are not in time phase. There is a phase difference. Okay, good. Now, how about a good conductor? Now you ask the question, how do we define a good conductor? Perfect conductor, we know sigma goes to infinity, but what is a good conductor? Yes, good conductor is the one where sigma is very large compared to omega epsilon. If sigma is very large compared to omega epsilon, then gamma becomes square root of j omega mu sigma, and square root of j is what? 1 plus j by root 2. Therefore, it's got alpha and beta numerically exactly equal, and what happens to that is equal to square root of pi f mu sigma, useful result. And what happens to eta, which is it's going to get very boring. I'm just going to keep pushing the slides forward. And phase velocity is omega by beta, which is square root of 2 omega by mu sigma. Is that okay? Yeah, you can substitute this beta and then rearrange the terms and show that this is indeed correct. It should be all right, I suppose. Yeah, it should be all right. No problem. And for copper, phase velocity turns out to be nowhere near 3 10 to the power of 8. It will be only 508 meter per second. Very slow. It is really slow. Wave will go inside copper very slow. And the next question is, how far do these waves go? We have an alpha which is numerically equal to beta. It is not a small quantity anymore. So we ask the question, how far it goes before the amplitude decays to e to the power of minus 1 times its original value. That is, Ex, the value of electric field at any point x, upon E naught, that is the value of the electric field at x equal to 0, when will it become equal to e to the power of minus 1? Of course, Ex by E naught is e to the power of minus alpha z. Therefore, at z equal to 1 by alpha, this will reach the amplitude of e to the power of minus 1. And this is known as the skin depth. It is the depth at which the amplitude of the field falls by e to the power of minus 1 or 1 by e. And this happens to be a very interesting number. Since alpha is equal to beta equal to square root of pi of mu sigma, you can compute skin depth as 1 upon square root of pi of mu sigma. And for copper, this will turn out to be equal to 0.038 millimeter at 3 megahertz. Notice, skin depth is a function of frequency. If the frequency increases, skin depth decreases. Therefore, at f equal to 10 gigahertz, you can show that delta will be equal to 0.66 microns. What is the advantage of this skin depth? It has multiple roles to play in life. One role, suppose you are trying to make electromagnetic waves penetrate through my body. How deep the electromagnetic wave goes depends on the frequency. If the frequency is low, it goes deeper. If the frequency is high, it doesn't penetrate deeper because of the skin depth. Now, in the second example, suppose you have a material made of a poor conductor, say I shouldn't say poor conductor, not a very good conductor. No, it's all playing with words, is it? Not a very good conductor example could be, let's say, steel. Steel is not a very good conductor. It is a conductor, but not a very good conductor in comparison with copper or silver. Now, if I want to improve the conductivity, I can give a coat of silver on it. But how thick the coating should be? Suppose electromagnetic waves from free space falls on silver coating, it penetrates into silver. How far it penetrates? Few skin depths. So the coating must be few skin depths thick. So physically, it depends on the frequency. If you are operating, let's say you give a copper coating, if you are operating at 3 megahertz, you need 0.03 or 0.04 mm thick one skin depth. Let's say if you want to have 10 skin depths, it will be 0.4 mm. Whereas if you're operating at 10 gigahertz, you just have to be 6 microns. It's a very thin layer that is good enough. It will ensure that the electromagnetic waves will not touch or will not see the base metal, which is not a very good conductor, like steel, for example. Now, let's get back to our visualization. Now you will be able to see the phase relationship, what happens in space for various types of media. Lossless case. Let's play a movie of this. Lossless case, electromagnetic waves propagating along the positive z direction, amplitude does not change, both electric and magnetic field are in phase with each other. Convincing? Okay. Now what happens to low loss medium? As the wave propagates, the amplitude decreases. Notice that the yellow trace or the red trace, it starts decreasing as the wave propagates deeper into the medium. So, and the electric and magnetic fields are almost in phase. Almost in phase. How do you recognize if the wave is in phase or not? Look at the zero crossing of the yellow trace and the red trace, and that will tell if they coincide, they are in phase. If they don't say coincide, they are out of phase. Now let's look at this one. Oh, not that. Yes, lossy and conductor. In case of lossy, if you notice here, the wave decays very fast. The distances here are all kept in meters, and therefore, and don't worry about the frequency. I think I chose what? I think the wavelength in free space was about 3 meters. Therefore, it is 100 megahertz frequency I've chosen. And if you notice here, there is a phase difference between electric and magnetic fields, right? Magnetic field is lagging the electric field. You can watch that here. In case of a good conductor, we'll see a similar behavior. Electric field and magnetic field, they decay very fast when they travel into the conductor, but this should be 2 10 to the power of -5 here, and it decays really fast. Few microns, it will just decay off. In this case, it will be few thousands of microns, few less than a millimeter. And if I play a video here, you will see very similar behavior. The field decays very fast as it propagates into the conductor. We hopefully will get to see this once again when we look at interaction between plane wave and a conductor, if you get a chance there.